Now let us compute some examples of Laplace transforms. So the first example is ft is equal to 0 for all t greater than 0. So this is an easy example. So here the Laplace transform ft, also written as fs, this is simply 0 times e to the minus st from 0 to infinity dt. So this is just the integral of the 0 function dt, and this is simply 0 using the linearity property of the integral. Okay. Here, notice that we can apply the linearity property, but we have to do it carefully, because if we write this as 0 times integral 0 to infinity dt, then this is an undefined integral. This is a infinite. This gives you an infinite value, so this will not be 0. I mean, we cannot use infinity times 0 equals infinity. Okay? We cannot use the formula 0 times infinity equals 0. So this is not a number. So what we do here is the following: that any integral of this form ft dt is by definition the limit as r goes to infinity integral 0 to r ft dt. So now we will use this formula with the limit concept to evaluate this integral 0, the integral of the function 0 from 0 to infinity. So let's see how this is done. So we can write 0 to infinity 0 dt as limit r tends to infinity integral 0 to r 0 dt, but this is limit. Now I can use the linearity property without any problems. Limit r tends to infinity 0 times r minus 0, okay, because let me write it one more step. So we get t, or rather another step, 0 times 0 to r dt. This is limit r tends to infinity 0 times t from 0 to r, and this is again limit r tends to infinity 0 multiplied by r minus 0, which is again r. Okay, so this is limit r tends to infinity 0 times r, but this is again 0, so limit r tends to infinity of 0, but this is now 0. Okay, so that this calculation can be formalized using limits. So one has to be careful when you have this kind of integral from 0 to infinity. It is always defined by this formula using limits, and this is what is called an improper Riemann integral. It's called an improper Riemann integral because the Riemann integral, as you know, can only be defined on intervals of finite length, like 0 to r here. So this function in the red parenthesis is a Riemann integral. But then you have to take an you have to take a limit as r tends to infinity, and this limiting process may or may not exist. And when you have to take a limit of on such unbounded domains, this is called an improper Riemann integral. I'll come back to this a little bit later, but let us first compute some more functions. Let me rewrite it again. ft equals alpha. Alpha is a real constant, and t is greater than 0. So again, we have the Laplace transform of this function. We have the Laplace transform of this function fs. This is an integral 0 to infinity ft e to the minus st dt, which is now integral 0 to infinity alpha times e to the minus st dt. Okay. Now I am going to use again this limit formula. So this is integral 0 to r, limit r goes to infinity, alpha e to the minus st dt. This can be evaluated, this limit, this integral inside the limit can be evaluated explicitly. First we use the linearity property, so this is the linearity property of the integral, by taking the constant alpha out of the integral. So we are left with the integral of e to the minus st dt from 0 to r. So this can be easily evaluated. This is alpha e to the minus st over minus s from 0 to r. Now this can be written as alpha times e to the minus sr minus e to the minus s0 is just 1 over minus s. Now it is easy to compute this limit, because if s is taken to be positive, then this term in the blue box, this will go to 0, okay, as r tends to infinity, because this is our graph of e to the minus st. So this is ft e to the minus st, y. This is x, this is y. And when y is equal to 0, it is 1. When x equal to 0, this is t. When t equal to 0, this is 1. And as t goes to infinity, it approaches 0. Okay. So it's helpful to keep these pictures in mind when you think about exponential function. When s is positive, then it goes to 0. However, when s is negative, then you have a positive coefficient in front of t, and then the graph looks like this. So this is yt e to the minus st, s negative, and this is for s positive. Okay. So this is the exponential function. When s is negative, it goes to infinity as t tends to infinity, but when s is positive, it tends to 0 as t tends to infinity. So here, in the end, we will get, after we evaluate this limit, we will get alpha times minus 1 over minus s. So minus cancels. So we are just left with alpha times 1 over s, or alpha by s, provided that s is positive. So this region of S where the Laplace transform is well defined, by well defined I mean a finite quantity, is called the region of convergence of the Laplace transform. So this is the region of convergence. Now let's look at another example. Ft is t to the power n, where n is a positive integer which is given. Okay. Again, our domain of definition is t greater than or equal to 0. Okay. Now let's try to compute this Laplace transform fs. So again, 0 to infinity, t to the n, e to the minus st dt. Now, for notational purposes, let me write this as fnt and capital Fn of s. Okay, so to keep track of this exponent n, I'm writing it as fn of s. So this is now limit r tends to infinity, integral 0 to r t to the power n e to the power minus st dt. Here we can use integration by parts, and you will see that integration by parts is a fundamental tool in computing the Laplace transforms. So here we will have the integration by parts by choosing our first function u as t to the power n and the second function v as e to the power minus st. Okay. So this is our u and this is our v. Let me recall again the integration by parts formula. So this is given by u integral v 0 to r, okay, minus integral 0 to r u prime, so the derivative of u, and then again the integral of v, and this has to be integrated with respect to t. Okay. So if we apply this formula, what will we get? So remember that we have a limit in front, and here we get t to the n e to the power minus st by minus s 0 to r, okay, minus 0 to r, the derivative of u is t to the power n, so this is n t to the n minus 1, and then again the integral of v by minus s dt. Okay, so here we get r to the power n e to the power minus s r over minus s minus, well, there is a minus sign inside the integral, so it will make it a plus, and I can take this n and this s out of the integral, so you get n over s integral 0 to r t to the power n minus 1 e to the minus st dt. Okay. Now note that the first term r to the power n, this first term r to the power n e to the minus sr, when you take the limit inside, limit is a linear operation, so you can take the limit term by term. So when you take this limit inside, you will get 0, because any power of n cannot grow faster than the exponential function, again provided s is positive. So provided s is positive, you will get 0 for this red bracketed term, and on the next term, so you get 0 in the first term, and the next term is n over s limit r tends to infinity 0 to r t to the power n minus 1 e to the minus st dt. Here note that this is again an improper Riemann integral, but here now we have a exponent which is 1 less than the one we began with. This is n minus 1, and we have a factor of n by s. Okay. So I'm going to rewrite this as a recurrence relation. So we started with fn of s, and we got n over s f of n minus 1 s, because note that this is the Laplace transform of ft, which is t to the power n minus 1 e to the, so this is the Laplace transform of fn minus 1. Okay. Now we have this recurrence relation fns is n over s fn minus 1s. So we can keep substituting for various values of n, and we get again n minus 1 over s fn minus 2 s. So in this way we get n times n minus 1 up to 1, over s to the power n, you will get n terms, and in the end you will get f0 of s. Okay. Now note that the numerator is just n factorial and the denominator is s to the power n. And note that f0 of s, what is f0 of s? f0 of s is simply the Laplace transform of f0 of t, and f0 of t is just 1 because it is t to the power 0. And we have already computed the Laplace transform of constant function. Now this is a constant function equal to 1. Okay. So the Laplace transform of the constant function 1 is just 1 over s. So in this way we will get n factorial by s to the power n plus 1. Okay, now that we have seen how the limit is computed, let me go back to the notion of the improper Riemann integral. So first, let me reiterate that the Riemann integrals are only defined for bounded functions on finite intervals of the form a, b, okay, where minus infinity is less than a, less than equal to less than b, and is less than plus infinity. So a and b are finite real numbers. Okay. Now whenever you want to evaluate an integral of some function ft over 0 to infinity, we define it. So this is a definition in terms of the limit r tends to infinity 0 to r ft dt. Okay. So first, this is an improper Riemann integral. So this is an improper Riemann integral, and we say that this integral, this improper Riemann integral, exists if this limit is finite. Is finite, meaning once you have evaluated this integral, from 0 to r, you get a function of r, and then you take the limit as r goes to infinity, and after you pass to the limit, you should get a finite value. Then we say that the improper Riemann integral exists. Now it may happen that even though this integral exists for all r, but the limit may not exist. Here we are implicitly assuming, when we are trying to compute the limit, that first of all this integral from 0 to r has to exist for this definition to make sense. So in the next lecture we will see some examples of improper Riemann integrals and where this limit can fail to exist, and we will give some sufficient conditions for this integral to exist, meaning that the limit should be finite for those sufficient conditions on these functions f. So we will see that in the next lecture. Thank you.